Hello and welcome. Tonight we'll be exploring one of the greatest engineering challenges humanity has ever imagined. Not how to reach Mars, but how to leave it. For generations, Mars has occupied a special place in our imagination. It has appeared in stories, paintings, science fiction novels, and countless dreams about the future. We picture towering rockets rising into the sky, astronauts taking careful steps across red dust, and distant sunsets glowing beneath a pale salmon-colored sky. It feels like the natural ending to one of humanity's greatest adventures. Yet the closer scientists and engineers look at this remarkable journey, the more they arrive at a surprising conclusion. The hardest part is not getting there. It is coming home. That quiet realization changes everything. It transforms the entire mission from a voyage of exploration into something much more delicate, much more carefully balanced, and in many ways, far more extraordinary than most of us ever imagine. So, find a comfortable place to rest, allow your thoughts to drift as gently as distant clouds, and let's begin our journey into one of the most fascinating engineering puzzles humanity has ever faced. When most people imagine a mission to Mars, they naturally picture the launch. The engines ignite. The rocket climbs into the morning sky. Months later, a spacecraft slips quietly into orbit around a distant world before descending toward its ancient surface. Then comes the moment everyone has been waiting for. The first human footprint presses gently into the reddish soil. It feels like the end of the story. But to the people designing these missions, that moment is something entirely different. It is the beginning. Imagine planning an expedition to climb the highest mountain on Earth. Friends gather to celebrate as you reach the summit. Cameras capture the view. Flags flutter gently in the icy wind. From a distance, it appears that your goal has been achieved. Yet experienced climbers know something that every beginner eventually learns. Reaching the summit is only halfway. The mountain does not become easier simply because you have arrived at the top. In fact, many dangerous moments still lie ahead. Your strength is fading. Supplies are running low. The weather continues to change without asking permission. Most importantly, you still have to find your way back down. Mars presents a similar lesson, though on a scale so vast that it almost escapes ordinary imagination. The red planet sits, on average, hundreds of millions of kilometers away from Earth. Even traveling at extraordinary speeds, a spacecraft spends many months crossing the silent darkness between the two worlds. Unlike a journey across an ocean, there are no islands waiting along the way. Unlike climbing a mountain, there are no rescue teams waiting over the next ridge. And unlike life here on Earth, there is no possibility of calling for immediate help when something unexpected happens. Once astronauts arrive, they are almost completely on their own. That simple truth quietly shapes every decision made years before the rocket ever leaves Earth. It is easy to think of a Mars mission as a long road leading outward. Engineers often imagine something very different. They begin by asking a much quieter question: how will the crew come home? That single question slowly unfolds into hundreds of smaller questions. How will they find enough fuel? Where will that fuel come from? How will their spacecraft survive years in an environment unlike any place on Earth? How will every machine continue working after months of freezing nights, dusty winds, and endless silence? Little by little, the journey begins to resemble an intricate chain rather than a straight line. Each link depends completely upon the one before it. If one breaks, every link beyond it becomes meaningless. This way of thinking is known as mission architecture, although the phrase itself sounds much more complicated than the idea behind it. Perhaps it is easier to imagine building a bridge across a wide river. No one begins by placing the middle section first. Instead, every beam depends upon strong foundations hidden beneath the water. Each new piece quietly supports the next until the entire bridge finally reaches the opposite shore. A mission to Mars follows a similar rhythm. The launch depends upon the spacecraft. The spacecraft depends upon life support. The landing depends upon precision. The return depends upon everything. This is why many engineers speak about Mars in a way that surprises the rest of us. Public attention often celebrates the first footsteps on another planet. Engineers quietly think about the final rocket launch, not the one leaving Earth. The one leaving Mars, because only that launch transforms an extraordinary visit into a successful round trip. Without it, the astronauts have not completed a mission. They have simply arrived somewhere from which they cannot leave. There is another quiet difference between Mars and every place humans have explored before. Throughout history, expeditions almost always kept one comforting possibility in reserve. If disaster struck, help might eventually arrive. Ships could sail, aircraft could fly, supplies could be delivered, people could organize a rescue. Mars offers no such reassurance. The distance is simply too great. By the time another spacecraft could even begin its journey, months would already have passed. The opportunity to leave Mars does not appear whenever people wish. Earth and Mars slowly circle the Sun in their own graceful rhythms, creating rare moments when traveling between them becomes practical. Miss one of those opportunities, and the wait may stretch for more than 2 years before another favorable path opens once again. That means every mission carries a quiet sense of commitment, unlike anything humanity has attempted before. There are no convenient second chances, only careful preparation, only patient engineering, only countless small decisions made years in advance, each one protecting a future that has not yet happened. And perhaps that is the most beautiful way to think about this remarkable journey. The story of Mars is not really about traveling farther than anyone has traveled before. It is about learning how to leave one world, survive upon another, and still keep a path open that leads gently back to the place we have always called home. As that idea slowly settles into place, another question begins to emerge almost naturally. If returning home is truly the greatest challenge, what is it about Mars that makes letting go so incredibly difficult? The first time you see photographs of Mars, it can seem strangely familiar. There are mountains that stretch higher than any on Earth. There are valleys so vast they could swallow entire countries. Dust drifts across open plains, while pale clouds occasionally float through a salmon-colored sky. In some images, the landscape at first glance it is, but Mars has a remarkable way of hiding its true character. It is imagined stepping outside without a protective suit, not because the temperature is cold, although it often is, not because the winds are fierce, although enormous dust storms sometimes circle the entire planet. The first problem would simply be the air itself, or rather, the lack of it, the atmosphere surrounding Mars. Yet this thin atmosphere creates another strange problem. On Earth, our atmosphere works quietly in the background every day. It slows falling objects. It supports aircraft. It helps parachutes blossom open like flowers. It cushions returning spacecraft as they descend from orbit. Mars does none of these things particularly well. Its atmosphere is too thin to provide the gentle support we enjoy on Earth, but it is still thick enough to create friction, heat, and unpredictable forces. Engineers sometimes describe this as one of the most awkward environments imaginable. Mars offers just enough atmosphere to create problems, but not enough to solve them. It is rather like trying to swim in water that barely reaches your ankles. There is enough resistance to slow every movement, yet nowhere near enough to keep you comfortably afloat. Landing on Mars has challenged every spacecraft humanity has ever sent there. Leaving it presents an entirely different puzzle. Although Mars is smaller than Earth, its gravity still holds firmly onto everything resting upon its surface. It is gentle enough that you might imagine taking long, graceful steps across the landscape, almost as though every stride becomes a slow-motion leap. But gentle does not mean weak. Gravity does not need to be as strong as Earth's to become an obstacle. It only needs to be strong enough to insist that every returning spacecraft must carry enough energy to climb back into space. And unlike climbing a hill, there is no opportunity to stop halfway and catch your breath. The journey upward must continue until the spacecraft reaches orbit once again. As if this were not enough, Mars introduces another companion that quietly follows every explorer: dust. At first, Martian dust seems harmless, soft, fine, almost beautiful beneath the pale sunlight. Yet each tiny grain has spent millions, perhaps billions of years being broken into particles far smaller than ordinary sand. Instead of rolling away like grains on a beach, this dust behaves more like an extremely fine powder. It slips into narrow gaps, settles upon delicate surfaces, clings stubbornly to equipment, and refuses to leave. Imagine returning from a walk through a dry field, only to discover that dust has found its way inside your watch, your camera, your shoes, and every zipper on your jacket. Now imagine that every moving machine you depend upon for survival must continue working despite years of that same relentless dust. It quietly settles onto solar panels, reducing the sunlight they receive. It gathers around joints and seals that must continue moving smoothly. Even the simplest task becomes a little more difficult when the entire world seems determined to cover everything with an endless layer of reddish powder. Time itself becomes another silent opponent. Mars experiences dramatic changes between day and night. As sunlight fades, temperatures can fall with astonishing speed. Then, as morning returns, the surface slowly begins to warm once again. Day after day, month after month, year after year. Every expansion, every contraction, almost too small to notice. Yet together they create an invisible rhythm that gently pulls and pushes at metals, seals, pipes, electrical connections, and mechanical joints. It is much like bending a small piece of wire. Once changes very little. Twice still seems harmless. But after countless repetitions, even strong materials begin to grow tired. Now imagine a spacecraft patiently waiting on Mars for years before it ever has the chance to fly. Its engines remain silent, its tanks remain full, its computers quietly watch over themselves. Meanwhile, the planet continues its endless cycle of cold nights and brighter mornings, asking every piece of machinery to endure just a little longer. And then there is distance. From Earth, we have grown accustomed to instant conversations. A video call travels across oceans almost effortlessly. A text message reaches another continent before we have time to lower the phone from our hand. Mars belongs to a different scale entirely. Light itself, the fastest traveler in the universe, still needs several minutes to cross the enormous space between the two planets. Sometimes the journey takes even longer, depending on where Earth and Mars happen to be in their slow dance around the Sun. That means astronauts cannot simply ask Mission Control what to do whenever something unexpected happens. By the time a question reaches Earth and an answer travels back again, precious minutes have already slipped away. In many situations, waiting simply is not an option. The people on Mars must become their own engineers, their own mechanics, their own doctors, their own decision makers. For the first time in human exploration, the crew would truly live beyond immediate help. This changes not only the technology they carry, but also the way every system is designed. Machines must think for themselves more often. Computers must make careful decisions without waiting for instructions. The astronauts themselves must become remarkably independent, solving problems with whatever tools happen to be beside them. All of these challenges might sound overwhelming when considered one by one, yet together they reveal something surprisingly beautiful. Mars is not trying to defeat us, it is simply being Mars, an ancient world with its own quiet rules, patiently reminding every visitor that surviving there requires understanding rather than force. And perhaps that is why the greatest engineering achievements are rarely about overpowering nature. More often, they begin by listening carefully, learning the rhythm of an unfamiliar world, and discovering how to work with it instead of against it. Only then does another quiet realization begin to emerge. If Mars makes carrying everything from Earth so difficult, perhaps the smartest solution is not to bring more with us at all, but to learn how this distant world might help us build the road that leads home. For thousands of years, every great journey began with a simple question: how much should we bring? A sailor crossing an ocean needed enough fresh water to survive the voyage. An explorer walking across a frozen wilderness packed food carefully, knowing that every extra kilogram would make each step a little more tiring. Even a family setting out on a long road trip thinks about fuel before turning the key in the ignition. The farther you plan to travel, the more carefully you prepare. At first, a journey to Mars seems no different. If astronauts will eventually need fuel to come home, why not simply carry everything from Earth in the first place? It sounds wonderfully straightforward. Pack enough supplies, pack enough food, pack enough water, pack enough fuel. Problem solved. Yet this simple idea quietly falls apart the moment engineers begin making careful calculations. Rockets live by a rule that almost seems unfair. Unlike an airplane, which burns fuel gradually, while the aircraft itself remains largely unchanged, a rocket must lift every drop of fuel it intends to burn later. That means fuel has weight, and fuel added to lift fuel also has weight, which requires even more fuel. That additional fuel also has weight, which demands still more fuel again. The problem grows almost like a snowball rolling downhill, becoming larger with every turn. Imagine carrying groceries home on foot. One small bag feels effortless. 2 bags require a little more energy. Now imagine carrying enough food for an entire year. Suddenly, the food itself becomes part of the problem. The heavier your load becomes, the harder every step feels. A rocket experiences something remarkably similar. Every kilogram added to the spacecraft asks the engines to work a little harder. Working harder means burning more fuel. Burning more fuel means carrying even more fuel before the journey even begins. It is a surprisingly stubborn cycle. Engineers have spent decades learning that there comes a point where adding more fuel no longer makes a mission easier. Instead, it begins making the mission dramatically more difficult. Returning from Mars pushes this challenge to an extraordinary extreme. The astronauts do not simply need enough fuel to leave the Martian surface. They also need enough energy to climb into orbit around Mars. From there, another spacecraft must carry them back across the enormous distance separating Mars from Earth. Every stage depends upon the one before it. Every kilogram carried from Earth quietly echoes throughout the entire mission. Perhaps another picture makes this easier to imagine. Suppose you are planning to build a small cabin deep inside a remote forest. One option would be to load an enormous truck with every brick, every wooden beam, every nail, every window, every tool, and every piece of furniture before leaving home. The truck would become incredibly heavy. It would consume more fuel, travel more slowly, and struggle over every hill along the way. A different approach might be much smarter. Bring only the tools that cannot be found elsewhere. Use the trees already growing nearby. Gather local stone. Build with materials waiting at the destination instead of transporting everything across hundreds of kilometers. Modern Mars mission planning follows a remarkably similar philosophy. Instead of asking, "How can we carry everything?" engineers began asking a quieter question: what already exists on Mars? That small change in perspective transformed decades of research. The atmosphere of Mars may be incredibly thin, but it stretches around the entire planet. The surface may appear dry, Yet scientists have discovered enormous reserves of frozen water hidden beneath layers of dust and rock. The planet itself begins to look less like an empty desert and more like a place containing useful ingredients, waiting patiently to be understood. This idea became so important that it earned its own name. Engineers call it the use of local resources. The phrase sounds wonderfully practical because that is exactly what it means. Instead of carrying every single ingredient from Earth, future explorers may learn to use the resources already waiting where they land. The idea is surprisingly familiar. A baker does not carry finished bread into the kitchen each morning. Instead, flour, water, and yeast are transformed into something entirely new. Likewise, a carpenter does not transport an entire house to a construction site. Individual materials are carefully assembled until a home slowly takes shape. Mars may ask humanity to think in much the same way. Instead of transporting finished rocket fuel across millions of kilometers, perhaps we should transport knowledge. Perhaps we should carry machines capable of turning the planet's own raw materials into something far more valuable. The more engineers explored this possibility, the more elegant it became. Every kilogram of fuel successfully produced on Mars would be 1 kilogram that never needed to leave Earth. And because less mass leaves Earth, the launch vehicle can become smaller. A smaller launch vehicle requires less fuel. Less fuel means less weight. The entire mission begins to grow lighter, simpler, and more efficient. It is a beautiful example of how solving one problem quietly solves several others at the same time. Of course, recognizing an idea and proving that it works are very different things. It is one thing to imagine making fuel on another planet. It is quite another to build reliable machines capable of doing so year after year without mechanics, replacement parts, or nearby factories. That challenge would eventually inspire one of the most fascinating experiments ever sent to another world. Not a rover searching for ancient rivers, not a drill searching for hidden rocks, but a remarkably small machine with an extraordinarily ambitious purpose. Its job was to answer a single question. Could Mars itself provide the first ingredient needed for humanity's journey home? The answer would not arrive through dramatic explosions or spectacular discoveries. Instead, it would come quietly, one careful breath of the Martian atmosphere at a time, gently opening the door to an entirely new way of exploring the solar system. For most of human history, explorers survived by learning to work with the places they visited. A sailor could not carry an entire ocean of fresh water aboard a wooden ship. Instead, new supplies were gathered whenever land appeared over the horizon. Farmers did not transport fertile soil from distant countries. They learned to understand the land beneath their feet. Even birds, as they build their nests, rarely carry every twig from where they were born. They patiently gather small pieces from the world around them until something safe and familiar begins to take shape. Again and again, nature reminds us of the same quiet lesson. The smartest travelers do not carry everything. They learn to use what is already there. As engineers began thinking more deeply about Mars, they realized that the same idea might hold the key to humanity's future beyond Earth. At first, this seems almost impossible. When you picture Mars, you probably imagine an empty landscape covered in rocks and dust. Not a place where anything useful could be made. Certainly not a place capable of producing rocket fuel. Yet appearances can be wonderfully misleading. Although the atmosphere of Mars is astonishingly thin, it still wraps itself around the entire planet. Every gentle breeze carries enormous amounts of a familiar gas, one that we quietly breathe out every day here on Earth. To us, it is little more than an ordinary part of the air. To an engineer planning a mission to Mars, it begins to look something else entirely. It looks like raw material. The challenge, of course, is that raw material is not the same as a finished product. A field of wheat is not yet bread. Iron ore hidden inside a mountain is not yet a bridge. A forest is not yet a wooden house. Nature often provides ingredients. Human ingenuity discovers how to transform them. This transformation may become one of the quiet miracles of future Mars exploration. Imagine arriving at a small workshop built on a lonely plain. Nothing dramatic happens. There are no roaring engines or brilliant flashes of light. Instead, fans gently draw the thin Martian air into a series of carefully designed machines. Very slowly, almost patiently, that air begins a remarkable journey. It is cleaned, it is concentrated, it is carefully prepared for the next step. Nothing appears spectacular. Yet every quiet movement brings astronauts one step closer to returning home. Several years ago, NASA decided that this extraordinary idea deserved a real experiment. Rather than waiting until humans finally reached Mars, scientists built a small machine to see whether the concept truly worked under Martian conditions. The machine itself was surprisingly modest, about the size of a household appliance. It sat quietly inside the Perseverance rover, traveling across an ancient landscape that was once shaped by rivers billions of years ago. Its purpose was wonderfully simple. Could it produce oxygen directly from the Martian atmosphere? The experiment became known as MOXIE. Its name sounds almost playful, yet the question it asked could influence the future of human space exploration. Again and again, the little machine inhaled the thin Martian air. Again and again, it quietly demonstrated that oxygen could indeed be produced on another world. It was an extraordinary achievement, but perhaps not for the reason many people imagine. MOXIE was never intended to produce enough oxygen for astronauts to breathe every day, nor was it designed to fill the tanks of a future rocket. Its real purpose was much gentler. It simply needed to answer one question: can this be done at all? And the answer, encouragingly, was yes. Yet that tiny word carries another story hidden inside it. Anyone who has ever baked bread understands this difference. The first loaf you bake in your own kitchen proves that the recipe works. It does not mean you are suddenly ready to supply every bakery in an entire country. Scaling something upward is often far more difficult than creating it for the first time. The same quiet truth applies on Mars. The oxygen produced by MOXIE represented only a tiny beginning. A future human mission would require not a little more oxygen, not 10 times more, not even 100 times more. It would require machines capable of producing amounts thousands upon thousands of times greater, while operating continuously, reliably, and almost entirely on their own. That is no longer a scientific experiment. It is an automated factory. And unlike factories on Earth, this one cannot simply call a technician when something stops working. There are no spare parts arriving the following morning, no engineers driving across town, no maintenance crews waiting outside the door. The factory must quietly continue its work through freezing nights, drifting dust, and endless months of solitude. The story becomes even more fascinating when another ingredient enters the picture. Early human missions will almost certainly bring a carefully chosen supply of hydrogen from Earth, not because Mars lacks useful materials forever, but because transporting a relatively small amount of hydrogen is far easier than transporting enormous quantities of finished rocket fuel. Once the hydrogen arrives, something remarkable becomes possible. The hydrogen meets the carbon-rich gas gathered from the Martian atmosphere inside a carefully controlled chemical process. Rather than imagining complicated laboratory equipment, picture two streams gently joining like small rivers flowing together. As they meet under carefully controlled conditions, they create something entirely new. One path leads toward methane, a fuel well suited for powerful rocket engines. The other produces water. And here, the story reveals one of its most elegant moments. The water is not discarded. Instead, it becomes another valuable resource. Using electricity, that water can be gently separated once again. Part of it becomes oxygen. Another part becomes hydrogen. The hydrogen quietly returns to begin the cycle again, while the oxygen is carefully stored for the future. Very little is wasted. Almost everything continues flowing through the system in a calm, repeating rhythm. It resembles less a noisy factory and more a carefully tended garden, where every season prepares the next. Future missions may take this idea even further. Instead of bringing hydrogen from Earth, explorers may one day collect frozen water hidden beneath the Martian surface. That possibility opens an even more remarkable future. The planet itself would provide nearly everything needed for the journey home. Air from above, water from below, human ingenuity connecting the two. When you step back and look at the entire picture, it becomes clear that making rocket fuel on Mars is not really about chemistry. It is about changing our relationship with another world. Instead of seeing Mars as an empty destination that constantly consumes supplies from Earth, we begin to see it as a place that can quietly support those willing to understand it. And once that idea takes root, another challenge naturally comes into view. Producing fuel is one thing. Trusting an unmanned factory to continue doing so for years before a single astronaut even arrives is something else entirely. By this point, the idea of making rocket fuel on Mars may seem surprisingly reasonable. The planet provides raw materials. Ingenious machines transform those materials into oxygen and fuel. The astronauts arrive. They prepare their spacecraft. Then they fly home. It sounds wonderfully neat, almost like following the instructions in a carefully illustrated guidebook. But hidden inside that simple picture is another challenge, one so important that it quietly changes the entire timeline of a Mars mission. The astronauts cannot be the first to arrive. Not if they hope to leave again. Instead, something else must make the journey first. Long before the first human footsteps ever press into the Martian dust, another kind of explorer must already be waiting. Not a person, not even a rover, but an entire automated factory. Imagine planning a visit to a remote cabin deep within a snowy forest. You know that winter will be bitterly cold, so before anyone moves in, you arrange for a heating system to be installed months in advance. You switch it on. Then you lock the door and leave, for years. When you finally return, you simply hope the heater has never stopped working. The comparison is not perfect, but it captures the quiet leap of faith hidden inside every proposed Mars mission. The fuel factory must land safely. It must unfold itself. It must begin working. And then it must continue working without interruption through countless Martian days and nights, all before the astronauts even begin their journey from Earth. That single idea changes everything. The mission is no longer simply about transporting people across space. It becomes an exercise in building trust. Trust in machines, trust in software, trust in engineering decisions made years earlier by people who will never personally touch the equipment again. Every morning on Mars, the factory wakes to another day of work. It gathers the thin atmosphere, processes it, stores valuable resources, checks its own health, repeats the cycle, again and again and again. There is something almost peaceful about imagining such a machine. No applause, no dramatic countdowns, only quiet persistence. The sort of patience we usually associate with nature itself. A tree does not rush its growth. A river does not hurry toward the sea. Likewise, the fuel factory simply continues its work, one careful cycle at a time. Of course, patience alone is not enough. Every factory needs energy. Here on Earth, electricity often feels almost invisible. You flip a switch, a light appears, charge a phone, start a washing machine, turn on a kettle. Power arrives so reliably that we rarely stop to wonder where it came from. Mars offers no such luxury. Every unit of electricity must be produced locally. Every hour, every day, for years. The simplest answer might seem obvious. Solar panels have powered spacecraft for decades. They are reliable, lightweight, and remarkably effective in the sunlight. Indeed, many robotic explorers on Mars have depended on solar energy with great success. Yet future human missions ask far more from their equipment than any rover ever has. A fuel factory consumes an enormous amount of electricity, compressing gases, moving pumps, producing oxygen, keeping computers running, monitoring temperatures. Every step quietly asks for power. Then Mars introduces an old companion we have already met: dust. A single dusty afternoon on Earth might leave a thin layer across the windshield of your car. You wipe it away without giving it another thought. Now imagine that no one is there to clean it. Day after day, dust slowly settles. Week after week, another fine layer appears. Month after month, sunlight reaching the panels becomes just a little weaker. The factory continues working, but perhaps not quite as efficiently as before. Scientists therefore explore another possibility. Instead of depending entirely upon sunlight, future Mars missions may carry compact nuclear power systems designed to produce electricity continuously, regardless of weather, season, or drifting dust. Unlike the enormous reactors many people imagine, these systems are intended to operate quietly, providing a dependable stream of energy for years at a time. They resemble a steady heartbeat rather than a roaring engine, always present, always working, always ready. Whether future explorers rely on sunlight, nuclear power, or some thoughtful combination of both, the goal remains exactly the same. The factory must never simply stop, because every hour lost is an hour in which fuel is not being produced. And fuel is not the only thing that must wait patiently. Once enough oxygen and methane have been created, they cannot simply remain exposed to the environment. They must be carefully cooled until they become liquids, allowing enormous amounts to be stored safely inside specially designed tanks. If you have ever watched morning dew forming on a cold window, you have already seen how temperature quietly changes the behavior of matter. Mars asks engineers to perform something similar, but on a far grander scale. The fuel must remain extremely cold for months, perhaps years, while the return rocket waits silently nearby. Keeping something that cold for such a long time is rather like trying to keep a block of ice frozen throughout an endless summer, without anyone opening the freezer to check on it. The storage system must constantly protect its precious contents from slow warming, carefully preserving them until the day they are finally needed. By now, another pattern may be beginning to emerge. Nothing in a Mars return mission stands alone. The power system supports the factory. The factory fills the storage tanks. The storage tanks prepare the rocket. The rocket carries the astronauts into orbit. Each step quietly depends upon the one before it. It resembles a row of carefully placed dominoes, though unlike a game, the goal is not for them to fall. The goal is for every piece to remain standing until exactly the right moment. Engineers often think about these relationships as a chain of dependencies. You do not need to remember the phrase itself. The picture is enough. Imagine a long suspension bridge stretching across a deep canyon. Every cable shares part of the load. Every support contributes to the whole. Remove just one important connection, and the strength of the entire bridge begins to disappear. A Mars mission is built in much the same way. Success is rarely created by one extraordinary machine. More often, it emerges from hundreds of ordinary systems quietly doing their jobs without drawing attention to themselves. Perhaps that is one of the most beautiful lessons hidden inside this remarkable adventure. History often remembers bold moments. The first step, the first photograph, the first launch. Yet those unforgettable moments are usually supported by years of quiet work that almost no one ever sees. On Mars, the journey home may begin, not with astronauts climbing into a spacecraft, but with a lonely factory, patiently, sunful. And if that factory succeeds, another remarkable machine, resting nearby in silent anticipation, may one day awaken for the most important launch humanity has ever attempted. By the time the fuel factory has quietly completed its work, another machine has been waiting patiently nearby. It has watched dust drift across the landscape. It has endured freezing nights and chilly dawns. It has stood through seasons that no human has yet experienced in person. From a distance, it may appear silent and almost forgotten. Yet every part of the mission has been leading toward this single moment, the rocket. Not the enormous launch vehicle that lifted away from Earth months or even years earlier. This one is different, much smaller, far quieter, hidden from the headlines that usually celebrate dramatic launches. But in many ways, it carries an even greater responsibility. This is the spacecraft that must lift human beings from another planet for the very first time. If it succeeds, the journey home begins. If it does not, there is nowhere else to go. That reality makes this one of the most carefully designed machines humanity has ever imagined. When we watch a rocket launch from Earth, we often see months of preparation condensed into just a few spectacular minutes. Technicians inspect every connection. Engineers examine every sensor. Teams rehearse procedures again and again. If a valve behaves unexpectedly, someone investigates. If a computer reports unusual data, the launch can be postponed. The rocket waits until everyone is satisfied. Mars offers no such luxury. There is no launch tower filled with engineers, no fleet of support vehicles, no teams walking beneath the rocket carrying clipboards and toolboxes. Once the astronauts arrive, they become the final inspection team themselves, and even they can only examine what is visible. Many of the rocket's most important systems are hidden safely inside, quietly waiting for the day they will finally awaken. Imagine buying a brand new car. Instead of driving it immediately, you leave it parked outside in a lonely desert. Not for a week, not for a month, but for several years. During that time, hot afternoons slowly warm the metal. Cold nights allow everything to contract again. Fine dust settles over every surface. Tiny particles find their way into the smallest openings. Rain never comes to wash them away. When you finally return, you have only one opportunity to turn the key. You hope the engine starts. The comparison is imperfect, but it captures something important. The Mars ascent vehicle must remain healthy long before it ever begins its true purpose. Waiting is part of its job. Every sunrise, every sunset, every quiet day becomes another test of endurance. Materials expand slightly as temperatures rise, then shrink again when darkness returns. Rubber seals slowly age. Lubricants must continue protecting moving parts despite years of exposure to an environment unlike any on Earth. Electrical connections must remain dependable through countless cycles of heating and cooling. Each individual change may be almost impossible to notice. Together, they become one of the greatest engineering challenges of the mission. Nothing dramatic has happened. Nothing appears broken. Yet time has quietly been asking every component the same patient question. Will you still work when the moment finally arrives? Even something as ordinary as dust becomes surprisingly important. Martian dust is extraordinarily fine. It settles almost everywhere. Over months and years, it can gather around joints, covers, moving mechanisms, and protective seals. Engineers work tirelessly to design equipment that resists this silent visitor. But complete protection is difficult. Dust is persistent. It does not hurry, it simply waits. Fortunately, careful engineering is often built upon exactly this kind of patience. Protective covers shield delicate components. Special seals reduce unwanted intrusion. Materials are selected not simply because they perform well today, but because they are expected to perform just as reliably years later. The rocket is designed not only to fly, it is designed to survive. Then comes the day that everyone has imagined for years. The astronauts climb aboard, the systems awaken one by one. Computers quietly check temperatures, pressure slowly builds. Electrical systems confirm that they are ready. Sensors compare thousands of tiny measurements against the values stored in memory. Almost every decision now happens automatically. Back on Earth, engineers watch with enormous anticipation. But they cannot simply reach out and intervene. Even light, traveling at the fastest speed nature allows, still needs precious minutes to carry information across the vast distance between Earth and Mars. By the time someone on Earth notices a problem, the rocket has already made its own decisions. The launch belongs to Mars, not to mission control. That idea represents one of the greatest changes in human spaceflight. For decades, astronauts have worked closely with teams on Earth. Questions could be answered almost immediately. Unexpected situations could be discussed together. Mars gently removes that safety net. The spacecraft must become remarkably intelligent. Its computers continuously monitor the health of the vehicle. They guide the engines, control the direction of flight, respond to changing conditions. All within moments. The astronauts themselves also become something more than passengers. They become engineers, pilots, and problem solvers all at once. Yet despite all this sophistication, one simple truth remains. There is no rehearsal. Unlike a concert, there is no practice performance before opening night. Unlike a commercial aircraft, there are no daily flights building years of operational experience. Every mission writes its own history. The engines ignite only once. The ascent begins only once. History often celebrates moments of great drama. A rocket rising through clouds, a flag planted on distant ground, a photograph that circles the world. Yet perhaps one of the most courageous moments in the entire Mars mission will be surprisingly quiet. A handful of astronauts sitting patiently inside a spacecraft, looking toward a pale sky, trusting machines that have spent years waiting beside them, trusting engineers they may not have seen for many months, trusting countless careful decisions made long before they ever left Earth. Because once those engines come alive, there is no longer any question about whether the journey has begun. The only question that remains is whether this remarkable machine can carry them high enough to meet another spacecraft waiting silently above the planet. And that meeting, graceful though it may appear from afar, demands a level of precision unlike almost anything humanity has ever attempted. As the engines continue to burn, the rusty landscape slowly begins to fall away. The familiar plains become smaller. Ancient craters soften into gentle circles. Towering volcanoes, once unimaginably large, begin to resemble quiet shadows stretching across the horizon. For the astronauts inside the spacecraft, the most difficult launch of their lives is finally underway. Yet reaching orbit around Mars is not the destination, it is only the meeting place. Long before the astronauts ever landed, another spacecraft quietly took up its position high above the planet. Unlike the ascent vehicle lifting from the surface, this spacecraft has been patiently circling Mars, completing one graceful orbit after another, hour after hour, day after day, month after month. Its task is simple to describe, but astonishingly difficult to accomplish. It must wait. And when the moment finally arrives, it must meet another spacecraft, traveling thousands of kilometers below. At first, this might sound almost effortless. After all, if both spacecraft are orbiting the same planet, surely they will eventually pass close to one another. In reality, space is far less forgiving. Orbiting a planet is rather like running on an enormous invisible racetrack. Imagine two runners circling a stadium. If they begin at different times, if they choose slightly different lanes, if one runs only a little faster than the other, they may continue circling for hours without ever meeting. Now imagine that the stadium is hundreds of kilometers across. The runners cannot shout to one another. They cannot stop and wait. They cannot simply step sideways onto another lane. Everything must be planned with extraordinary precision long before either runner reaches the track. A rendezvous in orbit works in much the same way. The spacecraft leaving Mars must climb into exactly the right orbit. Not almost the right orbit. Not close enough. The correct orbit. Its speed must be carefully controlled. Its direction must be carefully guided. Its timing must be almost perfect. Even small differences can slowly grow into enormous separations as both spacecraft continue racing around the planet. Perhaps the easiest way to picture this is to imagine trying to board a moving train. If the train is standing still, the task is simple. But if it is already moving at tremendous speed, every movement must be carefully matched. Too slow, and the train disappears into the distance. Too fast, and you rush past it. Spacecraft behave in much the same way, except there are no rails, no stations, only the silent pull of gravity guiding each vehicle around Mars. Throughout the history of human spaceflight, astronauts have become remarkably skilled at these delicate meetings. Spacecraft have docked with orbiting laboratories hundreds of times. Cargo vehicles regularly deliver supplies to astronauts living aboard the International Space Station. Yet Mars quietly changes the rules once again. Here on Earth, if something unexpected happens during a docking maneuver, engineers can offer advice almost immediately. They can study incoming data, discuss possible solutions, recommend adjustments. The conversation flows almost as naturally as speaking across a room. Around Mars, that comforting rhythm disappears. Signals still travel at the speed of light. But the distance between planets means every message arrives several minutes after it is sent. A conversation that would normally take seconds becomes stretched across long moments of waiting. If a spacecraft drifts unexpectedly, if a sensor notices something unusual, if the computers need to make a decision, there is simply no time to ask Earth what should happen next. The spacecraft must think for itself. Its navigation systems continuously measure distance, speed, and direction. Powerful computers compare thousands of observations every second. Tiny bursts from small maneuvering engines gently adjust the spacecraft's path. Each correction may change the trajectory by only a small amount. Yet together, these careful adjustments slowly guide two speeding spacecraft toward one another. There is something wonderfully graceful about this process. Contrary to what films often suggest, spacecraft rarely rush together dramatically. Instead, they approach with remarkable patience. The final distance closes almost gently. Hundreds of meters become tens of meters. Tens of meters become only a few. The closing speed becomes slower than an ordinary walking pace. It is less like two racing vehicles colliding, and more like two leaves drifting together on the surface of a calm pond. Eventually, the docking mechanisms meet. Softly, almost quietly, mechanical guides help bring the two spacecraft into perfect alignment. Locks engage one after another until both vehicles become a single spacecraft once again. Only then do the astronauts finally leave the ascent vehicle behind. For the first time since departing Earth many months earlier, they once again find themselves inside the spacecraft that will carry them across interplanetary space. Looking back through a window, they might catch one final glimpse of Mars below, the planet that challenged every skill they possessed, the world that demanded patience, ingenuity, and trust from every person who helped build the mission. From this distance, it appears peaceful, almost delicate. Its great dust storms cannot be seen. Its freezing nights leave no visible trace. The countless engineering challenges hidden across its surface disappear beneath a thin veil of reddish light. It is a gentle reminder that nature often conceals its greatest difficulties beneath extraordinary beauty. Before beginning the long voyage home, there is one more quiet responsibility. Everything returning from Mars must be handled with extraordinary care. Scientists have never found evidence that life exists on Mars today. Even so, they prepare with remarkable caution. Any rocks, soil samples, or scientific equipment brought back from the surface must remain carefully contained until experts have had the opportunity to study them safely. This careful approach protects both worlds. It protects Mars from unnecessary contamination brought by humans, and it protects Earth by ensuring that anything returning from another planet is understood before it becomes part of our own environment. It is a thoughtful reminder that exploration has always carried responsibility alongside curiosity. Only after every system has been checked, every hatch secured, every sample safely stored, does the spacecraft finally turn its attention toward the tiny blue world waiting far beyond the darkness. Home, still unimaginably distant, yet closer now than it has been for many long months. And as the engines prepare for one final journey across the silent ocean between planets, another thought quietly settles into place. Everything that has happened so far has depended upon a remarkable chain of success, each achievement resting gently upon the one before it. As the spacecraft slowly turns toward Earth, it is tempting to believe that the greatest challenges are finally behind the crew. The engines have lifted them away from Mars. The careful meeting in orbit has succeeded. The long journey across interplanetary space is ready to begin. From this distance, everything appears almost peaceful. Yet, if we quietly look back over the path that brought them here, another story begins to emerge. The return journey did not truly begin with the launch from Mars. It began years earlier, long before astronauts ever saw the planet with their own eyes, long before a rocket stood waiting on the dusty plains, long before the first kilogram of fuel was ever produced. The journey home began with a simple decision made on Earth, a decision to trust an extraordinary chain of events. Imagine watching a line of lanterns stretching across a dark valley. Each lantern shines because the one before it was carefully lit. If a single flame goes out, every lantern beyond it remains in darkness. A human mission to Mars follows much the same pattern. Every success quietly depends upon another success that came before it. The astronauts could not launch from Mars unless the return rocket had survived. The return rocket could not fly unless its fuel tanks were full. The fuel could not exist unless the factory had patiently completed its work. The factory could not operate without electricity. The power system could not function unless it had survived years of dust, freezing temperatures, and endless isolation. Every link quietly supports the next. Remove one, the entire chain comes to rest. Perhaps this is why engineers often speak less about individual inventions and more about systems. History sometimes celebrates a single remarkable machine. The first airplane, the first satellite, the first moon lander. Yet Mars asks something rather different. It asks hundreds of ordinary machines to perform extraordinary work together. A pump quietly moves gas through a pipe. A valve opens exactly when it should. A sensor notices the smallest change in pressure. A computer makes thousands of tiny decisions without anyone watching. None of these moments would make newspaper headlines. Yet together they create the possibility of bringing human beings safely home across millions of kilometers. There is something quietly humbling about that thought. Great achievements are often remembered for their most dramatic moments, but they are built upon countless invisible successes that happen long before history begins paying attention. Even today, humanity is already taking careful steps toward that future. The Artemis program is helping engineers learn how to live and work beyond low Earth orbit once again. New spacecraft are practicing longer missions. New habitats are being designed. New life support systems continue to improve. Meanwhile, another generation of rockets is being developed with the hope of carrying larger cargoes farther than ever before. These projects are often described as stepping stones. The comparison feels wonderfully appropriate. Imagine crossing a wide river by carefully placing one stone after another. No single stone reaches the opposite shore, yet together they gradually create a path where none previously existed. That is where Mars exploration stands today. Each mission answers another question. Each experiment quietly removes another uncertainty. Each successful landing, each improved engine, each new navigation system adds another carefully shaped stone beneath humanity's feet. Even so, important questions remain unanswered. Can an automated fuel factory truly operate for years without human maintenance? Can large quantities of rocket fuel remain safely stored through the changing Martian seasons? Can astronauts confidently rely upon machines that have been waiting for them longer than many scientific expeditions have lasted? Can every part of the return chain perform exactly as intended on another planet? No laboratory on Earth can answer those questions completely. No computer simulation, no matter how sophisticated, can perfectly reproduce every surprise Mars may have waiting. Eventually, the only place to discover the answers will be Mars itself. That realization is both exciting and deeply humbling. It reminds us that exploration has never been about eliminating uncertainty. It has always been about preparing wisely enough to face it. Looking farther into the future, engineers imagine technologies that seem almost dreamlike today, powerful engines that could shorten the long journey between planets, robotic builders preparing landing sites before humans arrive, machines capable of manufacturing replacement parts whenever something wears out, artificial intelligence quietly monitoring equipment day and night, noticing problems long before people would see them. Perhaps one day, small settlements will appear beneath protective shelters, where future explorers grow food, recycle water, and continue expanding humanity's presence beyond Earth. If that future arrives, it will almost certainly grow from the quiet engineering lessons learned during these first return missions. Not from a single breathtaking breakthrough, but from patient improvement, careful observation, thoughtful design, and thousands of small problems solved one at a time. When future generations look back on the first human expedition to Mars, they may remember the famous photographs, the footprints, the flags, the distant horizon glowing beneath a pale sky. Those images will undoubtedly become part of history. But perhaps the achievement that matters most will be something far less visible. The moment humanity proved that it could leave one world, build what it needed on another, and then find its way safely home again. There is a quiet kind of wisdom hidden inside that idea. Every journey becomes more meaningful when there is a path home, not because returning is easier than leaving, but because returning shows that we truly understood the place we visited. We learned its rhythms, we respected its challenges, we adapted instead of forcing our way forward. In doing so, Mars would no longer be only a distant destination. It would become the first world beyond Earth where humanity learned not merely to arrive, but to live, to prepare, and to return. And perhaps, as you begin to relax and let these thoughts drift gently through your mind, that is the most comforting realization of all. The future of exploring the solar system may never depend upon one giant leap. Instead, it may be built from thousands of careful, patient steps, each one somewhere beyond the darkness. Mars will continue circling the sun, Zeus patient, silent, unchanged, waiting for the day when human beings no longer see it as the end of a journey, but as one more place from which they have learned how to come home. Good night, and may your own journey tonight be a peaceful one.